Okay, so prior to break and everything, we were talking about blocking. And remember our activity we did in class, we talked about how a block is just one way that we kind of veer away from a completely randomized design and say, um, we may need to block other sources of variation that are not salient or important factors to us in the experiment, but we know provide a source of heterogeneity in the response that we need to control for. And so we talked about this slide in class. I brought it up because I thought it was complicated enough we needed to talk about it in person. However, let's review it again here. I think it's been enough time and is difficult enough. In the past, when we did all of our power calculations, the focus was all on sample size, right? As we increased our sample size, power increased. But if we are really trying to understand how we can improve variance and reduce heterogeneity or variance across our response, or the unexplained variance in our response, then we need to be thinking bigger than this. Making our sample size bigger isn't going to help if we have uncontrolled sources of heterogeneity in our response. Instead, if we can block out some of these sources of heterogeneity, then we can actually increase power substantially without actually having to make N bigger. And this is one of the payoffs and strengths of using blocking effectively in experimental design. So a principal tool in variance reduction is blocking. Think of a block as a homogeneous subset of units. These are units that prior to even running the experiment, we know that they're similar in some way, or we expect them to have some similarity. So think about when we talked about mixed models, how we talked about students within a classroom with a particular teacher will have some similarities just because of the classroom environment. Similarly, widgets coming off a machine where it's the same machine will have some similarity due to machine. So both classroom and machine, in that case, could be potential blocking factors. Other examples include similar soil, similar calibration used, similar batch of raw material from a particular region, say, similar operators, similar genetics, similar environmental conditions, similar socioeconomic background, something else. So here's kind of a crude visual, I would say. Say we have all of our units in this big circle. Okay, so this is all the units in this big circle, and then the blocks are similar subjects. So this might be, again, offspring from a particular mother make each block. And so there were 6 mothers and 6 groups of offspring, or students within a class, and there's 6 classrooms. Just a visual. It could be calibrations, for example. If calibrations are done on different days, maybe the calibration protocol is not followed exactly on each day, and so the effect of the calibration could be biasing your response in your experiment, and so you would block by calibration day. Blocking is some form of repeating the experiment. Either you can think of it as separately within each block, but also independently within each block. And so this does create a restriction on the randomization of your treatments to units. And so he makes I have a feeling you are all too young to understand this perhaps, but this is a Watergate reference. Follow the randomization. It's follow the money from Watergate. But we must always focus on that randomization. So different designs correspond with different randomizations. And following the randomization can help you understand the design. And this is really important and something that maybe isn't going to come real easy for everybody to do. Let's start with the first blocking design that we're going to take a look at. This is the simplest one. This is a randomized complete block design. We're going to have G treatments in this design and G units per block. So notice the randomization applies to each block. If we don't have a complete application of all levels of our factor within each block, then we do not have a randomized complete block design. That complete block refers to the randomization across each block, full randomization across each block. And so we'd have R blocks in this case, and so that's a total of N units, where N is R times G. So again, within each block, we randomly and independently assign our G treatments to the G units. So it's just like we do the application of our randomization units separately for each of those R blocks. And it's like a R single replication, CRD, all glued together. It's like a nice, I think of it as appended together, or maybe concatenated together, whatever visual works for you. This is complete because every treatment occurs in every block. It's not complete if every treatment does not occur in every block. The treatments could have a factorial structure, but then you'd have to have complete replication of all levels of your treatment structure within each block. Okay, so again, it's no more complicated if you have a factorial structure, except you need to just make sure you have completeness. Blocking should really be assumed, I think. If you know of some source of variability prior to experimentation, and that source of variability is just not interesting to you, but is not something that you can get around. Okay, it's not something you can just eliminate. Blocking is done at the time of randomization. It shouldn't be imposed later, or it cannot be imposed later. Finally, randomization in an experiment could identify it as a randomized complete block. Here's the model. This should be a plus. That's a mistake. So it's Yij equals mu plus the effect A. This would be your treatment effect, and beta is your blocking effect. Notice it looks like an additive model, and that's because we do not have interaction between our factor alpha and our blocking factor beta. That doesn't make sense because we're trying to block that source of heterogeneity from our block units. If we expanded this to a two-factor treatment design, it would simply be done this way. Here it's a little confusing because here beta is our blocking unit. We're just going in Greek alphabetical order. But now down here, beta is a second factor, and gamma is your blocking unit. Okay, but notice we have the complete factorial there, but then we have our blocking unit not interacting with our factorial units. The model assumes that the treatments have the same effect in every block, so the treatments and blocks are additive, not interactive. Assuming additivity doesn't make it true, but sometimes by especially taking a log transform, we can make it near true or pretty true. Because there's only a single observation for each treatment in each block, we can't distinguish between random error and that interaction between treatments and blocks. If we had multiple replications of each treatment level within blocks, then we could partition out. But that's why we can't have the interaction, because really, in this model, that error is that alpha-beta interaction, technically. Again, it doesn't matter here, just like we did with our introductory example in class. It doesn't matter if it's fixed or random. I sometimes like to think of it as fixed. Maybe that's kind of that old school part of me that thinks of it as fixed. Because most of the time, like we talked in class, most of the time it really should be thought of as random. If you're talking operators on a machine or the calibration or the teacher effect, those are all random. And so most of the time, probably random. Okay, this is the final slide for this set of notes. Why does randomized complete blocking work? Well, here's a few ideas. You're making comparisons within blocks. So you reduce your variation because those units within each block are very similar to each other. And then you make the combination of those results across the blocks. So it's a more powerful way of combining these results and takes into account that you have similarity within block. The treatment totals contain the same block totals. So your effects for the blocks cancel out when we look at the treatment totals. This is true for the averages as well, because we usually want to look at the treatment totals, but instead the means or averages. Okay, so that's a nice and good, actually necessary thing, right? Is that those block effects cancel out if we're comparing treatment averages. If they didn't, then we'd be not be comparing treatment averages. We'd be looking at treatment averages with some mixture of blocking effects mixed in there, which would not be relevant or good. Block to block variability is still part is still the total variability in the data. But we kind of make it disappear when comparing treatments by collapsing it into the error, more or less. Okay, we're going to stop here next, or start here next time about why we don't test blocks.